Hi everyone, in this video we're going to look at finding or evaluating triple integrals in spherical coordinate. Now recall when we learned about polar coordinate and double integrals, we said that instead of rectangles we would have polar rectangles. Quite similar to that, instead of box we're going to have what is called a spherical wedge in this case, which means the three parameters rho, theta and phi are going to be between some constants a, b, alpha, beta, c and d. And here's an image of what that looks like. So we have rho. The spherical wedge is not a rectangle. It has the rho, which is the distance from the center. That's along this red axis. Then along the purple axis, we have a change in theta and we have a change in phi. So if you look at the projections of these in the zy plane, what we have is a change of angle of delta theta, delta phi, and a radius of rho, which gives one of these side lengths as rho delta phi. And if you look at the xy plane down here in the projection, this is delta theta, and this radius is rho sine phi, which we obtained from the previous diagram, and so that this particular length becomes rho sine phi delta phi. And the volume of the wedge, if you compare the different dimensions of this, not really a box, it's a wedge, but what you have is a change in rho, that's this dimension right here. Then you have the rho delta phi, which is a dimension we found over here, and then we have the rho sine phi delta theta, which is the dimension we found in the third figure. Approximately the volume is going to be length times width times height. And so when you multiply this, you get this rho square sine phi term, which is going to be the equivalent of the additional r that we had in our cylindrical and in the polar coordinate system. And because of that, when you go from fxyz dv to polar coordinate, the first thing, again similar to polar, when we go from here to spherical, quite similar to polar, you want to rewrite the function in polar coordinates, and you have this additional factor of rho square sine phi. Now this diagram here shows you how one of the explanations of why the rho square sine phi comes in, but we will be looking at some more explanations later on when we learn about what is called general transformation to other coordinate systems. So for now, this is what we get as an extra, where E is a spherical wedge, where spherical wedge is basically something that looks like this right here, which is our fundamental unit in when we work with a spherical coordinate system, just as a box would be in a regular rectangular three-dimensional coordinate system. All right, so let's look at an example. Evaluate the triple integral of e raised to x squared plus y squared plus z squared 3/2 over the region of this ball, which is given by x squared plus y squared plus z squared less than or equal to 1, which is a solid sphere. So let's first draw what this looks like. So we have a sphere. Now we need to write this in spherical form. Writing this in spherical form means we gotta write how rho changes, we gotta write how theta changes, and we gotta write how phi changes. So let's try to understand what's going on here. First of all, how does rho change? So rho goes from 0 to 1. And that's basically going from this point to the edge of the sphere. So that's your rho. Next, we're looking at theta. Now, how is theta changing? If you look at any point over here, theta is doing one full circle of this form. So theta goes from, oh, wrong color, sorry. Theta does one full round, so it goes from 0 to 2 pi. Which already at this point, the radius and the theta has already given us the shell. So which means for phi only has to go halfway around. So phi is only between 0 and pi. So converting this to coordinate system, spherical coordinate system, this becomes e raised to, now in spherical coordinate system, x squared plus y squared plus z squared is rho squared. So this becomes a rho squared 3/2. Then we have the rho squared sine phi, which we always need, and the d rho, d theta, d phi. This goes from 0 to 1. This goes from 0 to 2 pi, and this goes from 0 to pi. So this becomes e raised to rho cube rho square sine phi d rho d theta d phi. 0 to 1, 0 to 2 pi, and 0 to pi. Now, as you can notice, this becomes separable now. So this breaks down into three integrals. This will be 0 to pi sine phi d phi, 0 to 2 pi d theta, and 0 to 1 e raised to rho cube rho square d rho. This can be worked out with a u substitution. If you do u is e raised to rho cube, by chain rule, the derivative is e raised to rho cube 3 rho square d rho, or 1/3 du is e raised to rho cube rho squared d rho. Now, when rho is 0, this is e raised to 1, and when rho is e raised to 0, which is 1, to e, and this is just 1/3 du. This is 2 pi. This is cosine phi going from 0 to pi. So cosine pi is -1 minus 1 is, this will give me a 2. So a 2 pi e minus 1 over 3. So this becomes 4 pi over 3 times e minus 1. Okay, so pretty straightforward, similar to polar coordinate, just making sure that you make the right substitution of x, y, and z values, and do not forget to add the rho squared sine phi at the end. Okay, let's look at the next example. Use spherical coordinate to find the volume of the solid that lies above the cone z equals square root x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals z. So here, first of all, what we need to do is we need to complete the square to get the equation of the sphere. X squared plus y squared plus z squared equals z is not a sphere equation that we are directly familiar with, but we can do the following. Complete the square with for z. So I can write z squared minus z as z minus 1/2 squared. This is z squared minus z plus 1/4. So to make them the same, I will subtract a 1/4. So what I have is x squared plus y squared plus z minus 1/2 squared minus 1/4 equals 0, or x squared plus y squared plus z minus 1/2 squared equals 1/4. So this is a sphere which has its center at x equals 0, y equals 0, and z equals half. But it has a radius also of half, so it exactly touches the origin here. That doesn't make it look like a sphere. Okay, so this is 0, 0, 1/2, and the radius is also 1/2. So now we have a sphere, which means, and it says explicitly to work with polar coordinate system, right? So we have, what is the equation of the sphere then in polar coordinate system? This is rho squared equals rho cosine phi, or rho equals cosine phi. So that's the equation of the sphere in polar coordinate. And what about the equation of the cone? Z equals square root x squared plus y squared is rho cosine phi is square root of rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. If you factor this out, you're going to get cosine squared plus sine squared, which is 1, and end up with rho sine phi. Okay, so that's the cone. So what is the shape we're dealing with here? Let's see. It's below the sphere and above the cone. The cone is here. This is the cone. So the area that we are working with here, or the region we are working with, is above the cone and below the sphere. So trying to find this volume. Now we know that when we are finding volume using triple integral, it's just 1 dv over E, but we are using polar coordinate system. So the 1 becomes, or the 1 remains the 1, but we have a rho squared sine phi d rho d phi d theta. Now what are the limits? Rho now goes from 0 to the cone, where cone is, or to the sphere, sorry, which is cosine phi. And where do these angles go from? These go from 0 to pi over 4 and 0 to 2 pi. Why is it pi over 4? It's pi over 4 because that's where this is given at phi equals pi over 4. The cone is described at phi equals pi over 4 because the equation is whenever rho cosine phi equals rho sine phi, or tan phi equals 1, which gives phi is pi over 4 in the first quadrant. So that gives us that particular result. Again, this can be broken down into 3 different integrals: 0 to 2 pi d theta, 0 to pi over 4 sine phi, and you have from the first one, the rho squared, 1/3 cosine cubed. So 2 pi over 3, 0 to pi over 4 sine phi cosine cubed phi d phi. Now whenever you have a mixture of sine and cosine as an integral, you will have learned something like this: a result about cosine to the power m and sine to the power n. I have it summarized over here. You can take a look in the notes. But the idea is if I use u equals, say, cosine phi, this will work out because du will take care of the sine phi. So I get 2 pi over 3, cosine 0 is 1, and cosine pi over 4 is 1 over root 2. And this becomes a negative. I get a du and a u cubed. So I get negative 2 pi over 3, 1/4 u to the 4, 1 to 1 over root 2, which is negative pi over 6, 1/4 minus 1, or 3/4 pi over 6, or pi over 8. So here there are some, these you have seen these before. These two formulations of cosine 2 theta give us these two important results, which is going to occur again and again and again. You'll have to find integrals of cosine squared, sine squared several times, and for this you always use the half angle formula. The other thing that you might encounter is cosine to the m and cosine to the n. If they are both odd, you can just use any of them and it works. If m is odd and n is even, we use sin x and use cosine x. If they are even, then we rewrite them using cosine squared plus sine squared equals 1. So try that out with different values, and that's that's it for this particular video. It's kind of short, and it's similar to just the only thing you gotta keep in mind is that make sure you don't forget to put the rho square sine phi whenever you are converting things into where is it? Oh, this converting things into spherical coordinate system. All right, that's it for this video. Thank you.